Can you hear me? Yeah, great. Yeah, today's topic is offensive security view to cross-chain bridge security. But before I introduce myself, I want to talk about numbers. Since 2022, more than $2.5 billion have been stolen from the cross-chain bridges, not from DeFi, not from wallets, directly from the bridges. And you can think that those cross bridges are the bank of Web3 ecosystem, and they run with the mixed code, servers, and humans. And the most interesting part is the most breach hacks were not caused by the smart contract vulnerabilities. It's happened somewhere else in APIs, in the validator operators, and the network infrastructure, and what we call Web 2.5 area. It's a gray zone between where Web 2 meets Web 3. And I'm Ece. I work in Hacken since 3 years now, and I have been working in this area for about 9 years. And in my daily work, I test the system that I mentioned before that stays gray zone area, like the mobile applications, web applications, browser extensions, desktop applications, source code analysis, including the gaming system. And at Hacken, we also conduct smart contract audits, layer 1 security, including we have bug bounty programs. And here's what we will cover today. We will start with basics, like how bridge actually work and what's inside it, why architecture matters, and what each one means for the security. And here, there's 3 questions we should ask. First one is the how does a bridge work? The other one is the what's the off-chain layer and what's the Web 2.5. Let's imagine 2 isolated islands. And left side is the Bitcoin and right side is the Ethereum. And each one has own rules, own protocols. They don't communicate each other. They don't interact with each other. There is no native connection between them, right? So the question is, how do you move your assets? How do you move your value one to another? So that's the where bridge came in. Most of the common mechanism is lock and mint. Say you want to use your Bitcoin on the Ethereum island. You sent your Bitcoin to the bridge, and bridge locks it, and no one can touch it. And you can use your Bitcoin as the wrapped token in the Ethereum island, just like any other user. And when you want to go back, you do it reverse. You wrap your Bitcoin, and it gets automatically burned. The lock site opens, and your Bitcoin is back. Now, look at the bottom of the picture. Who actually approves the lock? Who actually approves the burn? Who decides that the message coming from one chain is valid before another chain acts on it? You know, it's the validators, it's the API, the network infrastructure, the private keys. So that's why we called Web 2.5, not fully decentralized like Web 3, and it's not the traditional Web 2. It's somewhere between them, and they carrying the risk from one world to another. And this brings us to the most important point of the section. Because the weakest point is the validators. They live in the Web 2.5 area. They can be manipulated, they can be tricked, they can be taken down. So they can be compromised. So, and every major hacks we have seen so far, like Ronin, like Harmony Horizon, didn't happen the on-chain side. The on-chain side was fine, but the off-chain layer was broke. But not every bridge works the same way. Look at the table. There are 4 different models and there are 4 different trust assumptions. First one is canonical. It trusts the chain itself. Minimal 2.5 attack surface, but the speed is really slow. The other one is the validator. It trusts human and keys, and minimal it's high Web 2.5 attack surface, but it's also very fast. The other one is the proof base. It trusts mathematics and the ZK proof. Low 2.5 attack surface, but it's really slow and expensive. By the way, the industry is moving here, but not just fast enough. The other one is the liquidity. It trusts layer and attack surface is medium to high, and it's really fast and user-friendly. So at the end of today, the pattern is clear. 3 out of 4 models have Web 2.5 exposure. Proof base is still evolving, but until that changes, billions of dollars keep flowing through the off-chain sites. Now, let's see what happens when attacker actually find it. I believe you already know that attack, the run-in attack, it's conducted by the Lazarus group. They spread phishing attack, developer targeted via fake job offers, and the private key extracted from the local machines. And as a result, 625 billion has gone, and the chain never knew that. The other one is the Harmony Horizon. Same result, but different path. Server infrastructure compromised directly, and they only need 2 keys, and 100 million has gone. The other one is Shalihulut. Actually, this one is the most smartest hack I have ever seen so far. It's a self-spreading worm, and the story behind that, the attackers hacked the npm validators, and then they upload their backdoors to the trusted packages. So as a developer, when you run the npm command, it's automatically the worm in your machine. So yeah, you were already hacked. And the interesting part is it's affect almost 3 layers, like Web 3 area, Web 2 area, Web 2.5 area. In Web 2 side, cloud server was compromised, and in Web 3 side, the validator keys, the environment files, the credentials was taken from the developer's local machine. And the Web 3 side, the attackers used that stolen credentials, and they upload the fake version of the trusted Chrome extensions, and users who logged in, their wallet data was stolen silently. And it's nearly affect 20 million users right now, and the effect is still going on. Like I heard yesterday that 2 Axios version was affected from them. The fixes come the same day, but if you are using the older versions, or just be careful about and aware of it. And let's map the attack surface systematically. There are 5 issues here, and each one is positioning on the off-chain side, but they are also affect the on-chain side directly. First issue is the cross-chain message spoofing. In here, every chain has a fundamental question that needs to be answered. The question is, did the log actually happen on the other chain? Because an attacker sends a crafted breach messages, and the chain accepts these assets without a wallet transaction on source chain side. And look at the attack flow. Attacker submits the crafted breach messages, backend accepted this message as valid, And third section, there is no cryptographic commitment writing to this message to a real on-chain event. So there's no signature verification. And as a result, Mint executed on and you gave unauthorized assets. This is the basic request you can see. These are our main playground, endpoint, headers, and the functions. And look at the TX hash. It's fabricated, nothing was ever logged in the Ethereum side. And there's a signature verification, but the field exists, but it never checks what's inside it. So as a result, 1 million wrapped token minted for nothing. Just the message here said that trust me. And the other issue, and here's something worth pausing on. Let's say smart contract is perfectly written and the signature verification is solid. Does it mean you are safe? No. the answer is no, because the attacker doesn't go through the legitimate flow. They go directly through the API. They craft the message, and the API passes to relayer, and relayer passes the smart contract, and the smart contract assumes that this message is valid and the signature is valid, and you automatically got approved. So the main problem is that there is no defense in depth mechanism. So every layer needs own control. So smart contract doing its job doesn't mean that the API layer is doing its job. So Web 2.5 is just the additional attack surface, so you can bypass on the on-chain layer. But the other main problem is here there's a disconnect between the on-chain and off-chain side. So the teams working on these parts needs to be more aligned, more aware, like what each side is doing. And it's really easy to prevent, but that's why this kind of issue becomes more possible today. The other one is the replay attack. Replay attack is basically when someone takes a valid transaction and just sends it over and over again. The system keeps paying out every time, and it happens because the bridge doesn't track what's already proceed. So it treats the same request. It's like it's a new each time, let's say. So this is let's walk through this. This is a simple request and response. The real claim exists. The attacker doesn't create a fake one, just to duplicate the same request, same TX stage, same signature, same amount. Field can be changed by the way, and sent it again, and the bridge gets it and checks the signature is valid, checks the amount is valid, but it's never asked, did I already proceed this before? So there is no nonce here, there's no tracking in here, so it pays out again and again, same transaction, and second payout and third payout. The fix is actually really simple in here. Every claim should be tied to a unique identifier, like the nonce, like the TX hash, like the registry or the message ID. So in short, replay protection must be enforced to the bridge logic level. So this one is different from everything we have seen so far. Let's say you logged in some of the JAX platform, and each platform assigns you an ID. And imagine your user ID is 1. When you view your own profile, you can able to see your personal details like the user ID, username, QIC status, or the sub accounts. But the problem is here, when you change your user ID 1 to 2, you can able to observe the other user's data. And it means that you can effectively enumerate all the user's data stored in the system. So this is you have only read access, but this is what we called as the vertical leader scenarios, and there's also horizontal scenarios. But in horizontal scenarios, you can able to modify the other user's data. The other issue is the unauthorized universal transfer. Let's say the attacker is using their own wallet session. So the authorization header is completely belongs to the attacker. However, in the transfer request, they have set the from account field to the victim ID, victim's wallet address, and as a result, they simply reuse the wallet address they were able to observe in the EDOR issues. The core misconfiguration here, the system only checks whether the wallet exists, but never verifies who actually belongs to. Because of that, you can change the wallet address here. You can take the funds others users' wallets. So the authentication and the authorization are two different things. Authentication answers who are you, and authorization answers what are you allowed to do. In that scenario, the authorization header is valid, but it never asks the who belongs that authorization header. And the other one is the social engineering attack. This attack is become very popular lately. The attackers group reach out to developers on LinkedIn via fake job offers. And the conversation feels natural, the interviews and technical talks, everything looks professional. But then comes the technical challenge. They send you a coding task, but hidden inside the coding task is a backdoor. So while you are working on this challenge, the attacker already has access to your machine and quite stealing everything in your local. And what makes this especially dangerous, it's how they target it. They profiling the persons, users, and they build the whole approach around that one person. And like whoever the most likely have the validator keys on their machine, they target that person. And once you download the task locally and start solving the challenge, you got automatically hacked. And last one is it's mostly related to Web 2 infrastructure, but it's directly affect the Web 3 area. On July 2024, most of the several DeFi protocols were affected with DNS hijacking attacks. The breach code was clean. There's no issue in the on-chain and off-chain logic. However, the attackers came from the off-chain side. The money register account has no factor authentication. So the attackers runs a simple DNS lookup command. And with one command, they can able to observe the provider, region, namespace, register, and there's no DNS sec in here. And the attacker gets into register account like credential stuffing, brute forcing, or two-factor authentication bypass. It depends of the system and the attacker's mind. And they changed the DNS record. And at the end of the day, the site looks identical, same logo, same UI, same colors, but the approve button calls the smart contract, attacker smart contract. So when you click the approve button and you confirm, you just gave you an access to the attacker, so it means that your all tokens gone forever. The attacker drains able to all the users' wallet in the system. So thank you for listening to me today.
We can take questions.
I think that's
Okay,
all.
thank you.
Yeah.